So our next talk is Tristan Croll, who works with Randy Reed's group in Cambridge, and he's going to be talking about his environment for interactive model building.
Okay, so am I on? Sounds like it. Okay, so I'm going to talk to you about today. It started a number of years ago in a completely different environment, well, both geographically and in software terms, back at the Queensland University of Technology in Australia. But what I'm going to show you today is my brand new version that I've been building over the last 6 months or so after coming here. The name of my package is SOLDE. As you can probably guess, the acronym came first, and then I essentially made up words to fit it. It stands for Interactive Structure Optimization by Local Direct Exploration, but I'm sure no one really cares. Anyway, so essentially, the challenges of low resolution, and I mean, so the examples I'm going to show you here are actually all crystallographic maps, but what I'm trying to do is make what I'm doing as agnostic as possible to the source of the map that you're actually trying to fit. But when you've got nice high resolution data, and I'm talking crystallographic high resolution here, 1 angstrom, 1.5 angstrom, all your problems are very, very local. Oops. And so to highlight what I mean here, a little video of a 1.5 angstrom data set, and what we're looking at here is a cis-peptide bond, which is beautifully shown in the map, that is absolutely supported right next to a threonine rotamer that's wrong. So just the way these things go. But you can see where all the problems are very easily. They're very, very close together. You can see the solution essentially immediately zoomed in. But when you zoom out like this, just a bit further out, you've got this whole problem. You can't see the forest for the trees. You get lost very, very easily. When you get to lower resolution, that starts to become a real problem because those maps just aren't giving you that information anymore. And so rather than asking the question, is this the right rotamer, you're suddenly asking, is this even the right residue that I have here? Is this density that I'm looking at here the backbone, or have I just threaded it through the side chain of a tryptophan? Or does this loop have 4 residues in it, or does it have 6? And so an example here is actually the one that essentially started me down this path some years back, is a structure, 3.8 angstrom crystal structure solved in 2007. You're actually looking at a real serious problem area, but trying to tease it out is an absolute nightmare. And so it's 3.8 angstroms. It's a very complicated region because just up above there's a dimer interface, a biological dimer, but also a crystal interface. Down here there's not 1, not 2, but actually 3 non-specific crystal contacts all messing it up. And there was a fibronectin domain that at the time had no homology model, so it was all threaded by hand. And it's gone very, very wrong. But with your standard visualizations, that becomes very, very hard to see. And so one of the things that I've been really playing with, one of the first things I've been keen on doing, is simply working with new visualization modes, getting rid of this dichotomy of visualization versus model building and bringing them together so that you can actually see the problem that you actually need to fit. So starting point, first thing that makes things easier to get some idea of what needs to be done here is, well, two things are going on here. First, I've added a cartoon representation to actually give you some idea of where the backbone's going, but keep it nice and thin and out of the way so it doesn't get too much in your face. But also add a second level to the map in a surface representation so you can see your high density and your low density at the same time. Now, when you look at this, you start to get some better idea of what's going on, except you've still got all this other stuff in the way. You know there's a problem in there, but you're still trying to see the forest through the trees. So the next step to do is simply cut all of that away and find ways to very, very quickly narrow in on a specific region. so in this case, I've made a selection of all the atoms highlighted in green and provided routines so that you just at the press of a button, you mask your maps down to that, you hide all the atoms surrounding it, and give it just enough context to give you some idea of what's going on. And in this case, especially once it gets mobile again, you start to get a much better idea of what's going on. And here, what you can see in this loop here is the true path of the backbone. And what's gone on is that they've actually gone sideways out here through the density that actually belongs to a disulfide bond, gone up the density belonging to this other chain, and then jump back into their own density. And what's coming down and going back up there is where this little tail end should actually be going. And so that's via any traditional technique, what you would most likely be doing in this situation is tearing that whole section down and rebuilding from scratch. That's not what I want to do, though. I'll just let that finish. So the structure in question here, I don't think I've actually named it yet. That's actually the insulin receptor, and we just published the revised structure using the methods that you'll see in a bit. When was it? Early 2016. Yes. So visualization is one of my big things, but seeing a problem is and being able to see the solution is only half the problem. Now you actually have to fix the thing. So the other challenge I want to overcome is finding ways to actually fit this sort of data where you no longer have the map telling you where every atom needs to be. You need a lot more restraints going on. Now, traditionally, your model building packages are built for the computational capability that was available at the time. And so they keep things local, keep things simple, which is all you need when you have nice high-resolution data. So if you consider just the bonded interactions of this purple atom here, you've got 3 bonds to deal with, three bond lengths to refine. You have 3 angles and 4 torsions. The rotations this way, etc. But that's computationally cheap, which means you can do it on, well, you could do it on an early 2000s, late 90s computer with no big trouble. But it does rely very, very heavily on your dataset information to actually prevent all those non-bonded interactions becoming troublesome. And it starts to become more and more frustrating as your resolution degrades, as I'm sure many people here know. But because of all of that, if you actually look, and again, this is crystallographic data, but I have looked at a rather large number of EM structures, and the situation is more or less the same. But as of 2015, October 2015, this was all the 3 to 4 angstrom X-ray structures on the protein data bank. On the left, we have the Ramachandran outliers. In the middle, we have the side chain outliers. And then the clashes on the right, and these dotted red lines on the bottom are your standard cutoffs for what you would consider good in a high-resolution structure. So there's a lot of room there for improvement. The question is how to actually do that. And the approach I've been working with for some years now is molecular dynamics flexible fitting, but in particular turning it into something interactive. So with molecular dynamics, now you're including the non-bonded interactions around this atom. And computationally, this is a challenge. It's exponentially bigger, because for a 10 angstrom shell of atoms, which is typically in the range of what you need to actually get a realistic picture of the electrostatics around this guy, now instead of 10 parameters, you're talking, well, there's 790 non-bonded interactions with just this one atom. So yes, computationally, that's very, very expensive. And up until 5, possibly 10 years ago, if you're rich, would have been impossible to even consider doing interactively. But with the advent of GPU computing, that's getting much faster, much easier. Now, so the molecular dynamics flexible fitting is certainly not my idea. That arose some time before I ever started looking at this sort of thing. But it takes your electron density map, converts it into essentially a potential energy map. And so the atoms feel forces proportional to the gradient of the map where they happen to be, so it's like a ball rolling down a hill. If it's out in the middle of nowhere where there is no density, no gradient, they're just behaving as normal. They hit the edge of an energy well and they fall into it. Now, in terms of actually how this runs, I'm getting ahead of myself. Now, personally, I've always really enjoyed working with it truly interactively, using a 3D haptic interface device. I use this particular guy, it's called the Novant Falcon, which unfortunately isn't sold anymore, but there's a number of different alternatives that are drop-in replacements for it. There's numerous advantages of this. The force feedback, turns out, I find is actually really useful. When you pull on an atom, it's actually telling you by direct physical force whether you're pulling it in a direction where it wants to go or not. But also just being able to pull in 3 dimensions so that you can see where you want to go and move where you want to go at the same time turns out to be very, very valuable. So my overall aim with all of this is to make this task of model building feel like essentially playing with a real-world physical object. Trying to make it as if you could blow your protein up to the size of the room and just reach in and actually move atoms as they need to go. To help with that, as well as the 3D haptic interface device, I'm working on, of course, allowing you to pull atoms around with the mouse, but also lots of script-driven forces to actually drive configurations. An example of which you'll see in a little bit. And it's almost paradoxical, I guess, but the more physically reasonable restraints you add, and these non-bonded interactions are essentially a form of extra restraint on your simulation, the more freedom you actually have to interact with this thing, because it won't let you pull things into configurations that are truly wrong. It won't let you create atomic clashes. And if you pull it into something that is very energetically favorable and let go, it'll go straight back to where it was. Now, without much further ado, I'll show you an example of this in action. This was actually recorded on Sunday in my brand new environment. It's actually a repeat of the original insulin receptor job that started me on this, so it's cheating in a sense that I already knew where everything is meant to go, but I hope it will give you a good idea of how this is actually meant to work. So we're looking at this thing. We start our little local simulation. We have these all around it. We have a shell of atoms that are rigidly fixed in space, so that no matter what you do, it can't get out of contact with its surroundings. All these atoms are being pulled into this map. That little green cone is my haptic device. I just grab atoms, pull them, and they're constantly trying to fit themselves back into this map as I go. So you can, and because of all these restraints, you can get essentially as aggressive with this as you like. If you've got this big region, you basically just pull things out here to get them back roughly to where they need to go. Start refolding these things into place. You can see probably that this actually really needs to be a helix. I will be adding the tool so that you can select a region of this and just simply tell it to become a helix, and it will go there. That was actually present in my previous version. It's just something I haven't quite gotten around to adding to this version yet. So lots to see there, I guess. But I don't know. Do you want to see a little bit more of that, or will we move on? it goes on for another minute or two, but it's essentially the same job. We grab that tail end, pull it up into there. This guy needs to move in register here, and again, that's something it is actually fairly easy to add scripted forces to help you move, for example, a beta sheet in register. You just set position targets for the atoms in the new positions where they need to be and have it move for you, and then you just tinker around the edges to actually help it fix itself. Other things you may notice if you're a little bit eagle-eyed is the C-alpha atoms. So the atoms at the base of each side chain are little spheres that are changing colour from green to yellow to red. And that's actually the other thing that I'm really, really keen on making work in all of this, and that's my first example of this, is this live validation. So taking validation such as the Ramachandran plot, which is what those are actually denoting, and turning them into something that is just an ongoing visual guide. So you don't have to stop, check the plot, find the table of outliers, find the residue, go back, see if you've actually improved it or not. But you just get this real-time feedback. As I change this conformation, am I pulling it into an unfavored configuration or not? And so I've got the Ramachandran plot here. I mean, you see it updating here. The update is actually a lot faster than what you see. I'm only doing it once every 10 frames, but for a simulation this size, a few hundred residues, it takes 2 milliseconds to actually to recalculate the outliers. And then you click on any outlier there, it'll take you to that. And you can start a little local simulation to actually try and figure out what exactly is going on in that position. Yeah, I don't want to go too far ahead of myself, so I'll move on from there. Actually, no, I won't, because this is where I wanted to say that. So this was my first example of this, but the code that I've used to do that is I've split out and been talking to the folks behind mold probity to turn this into essentially a live version of most of the standard mold probity validation metrics. So your rotamer outliers, if you're working with RNA, the sweetness score, and then your Kablam scoring system for specifically for low resolution data that follows the C-alpha trace and predicts whether you're actually in a realistic conformation or not. Eventually, all of those things should be similar live visualizations. The other things, so scripted forces and restraints I've mentioned a few times. At the moment, that's essentially been on my to-do list as much as anything because it's actually quite easy to do. The last few months in particular, I've been adapting the Clipper Python to actually provide symmetry, native symmetry handling to all of this. But as a first example of the idea, well, here's an example of a cis-peptide bond that shouldn't be here, out on this loop, unsupported by absolutely anything. So you've got the visualization there, the now standard filled-in U-shape to show this is probably wrong. But to fix this, this is a sort of thing that should be trivial and I want to make trivial. So here, for example, I've already I have a table that will list all of these. You click it, it'll take you to there and select that residue. Click one button, it will start a new simulation around that area, which takes a few seconds to do. Then pause that, select one of the atoms in that cis-peptide bond, and click a button and blink and you'll miss it. It's now trans. And something I haven't mentioned is that in all of these simulations, I have restraints in place that will keep the residues in their the peptide bonds in their current cis or trans conformation until you tell them to be otherwise. So any of these you can flip on command. So similar applications of that is that some of which I have previously implemented and just need to re-implement in this new environment is dial-up a rotamer. You pick a residue, see a preview of what the rotamer will look like, but don't actually commit it yet, unless, you commit it if you like, if it's not clashing with anything, but often you have the case where your new rotamer is going to be overlapping with something else that's also wrong. In that case, you can just set that as a target and then have the simulation go there and have everything adapt to it as it goes. Similarly, register shifts, whether it's a beta strand or a helix, where your structure is fundamentally out of position. You can do it, especially with beta sheets, you can do it just by grabbing one end and pulling, and everything does tend to settle itself quite nicely, but often it's easier to actually have the software help you do it, especially when it is a helix, where things get a little bit trickier. Things I would love to add are things like prediction of loop confirmations and again, use the prediction from your server or from your software as simply a target for the simulation to go to, so that everything gets a chance to relax, rearrange itself as you go. And then situations, actually like something, if we start this one again, you'll see good examples here. Me playing around with the mouse, pulling the backbone around, where the environment, well, you can see an example of the environment really helping you in that you try to pull it into a conformation that it doesn't want to be, it will simply go straight back to where it was, telling you quite clearly that that's not favourable. But sometimes it goes back there simply because the surroundings are wrong. In that case, you may actually want to temporarily say, okay, let's pin this here while we do something else around it, and then turn those restraints back off. So there are lots of tools like that to be added over time. So the features it now has, as of a few weeks ago at least, is the native understanding of symmetry using the new Clipper Python libraries, and thanks to the team for doing that. For getting the Clipper Python project started. At the moment, that's crystallographic symmetry, but I want to eventually have it handle non-crystallographic symmetry like you'll find in the EM maps in essentially the same framework as crystallographic symmetry. With the same sort of seamless handling of maps and, of course, the actual symmetry contacts between your asymmetric unit and its neighbours. Current limitations, this is probably the biggest one right here. Right now, it's protein only. That's simply a limitation of the libraries I'm using to handle the MD is OpenMM. Only ships with protein topologies. And it's something that can be added to quite readily with all the different MD topologies out there. It just hasn't been done yet. Doesn't yet have any capabilities for building. That's something I definitely want to add. So actually adding residues, adding stretches of residues at a time as you need to. So essentially you need to have a model already in place, whether auto-built or a homology model or a molecular replacement solution, depending on your task. I have no real plans for alternate conformation situations at the moment. If your resolution is high enough to have those in it, you probably don't need my package for that job. The actual implementation, the graphics environment is Chimera X. This is the brand new and definitely improved in many ways molecular graphics system from the people behind Chimera over at UCSF. It's currently in alpha, evolving very, very rapidly, and SOLDE and Chimera X are kind of evolving in parallel to each other. The molecular dynamics engine is OpenMM, which has the most flexible Python API of any molecular dynamics code I've ever come across, and has been wonderful for making this all possible. The map symmetry handling is Clipper Python. And the validation is an application of the mole probability data sets. So just to wrap things up, some examples of the structures I actually have published in this now. So the first one was the insulin receptor in collaboration with Mike Lawrence, the original author of the original structure, using a higher 3.3 angstrom data set that he had actually on the shelf. So in total, we corrected 5 beta strands within that structure, which most of which turned out to be quite important. 2 of them were actually in what is, you might call the key dimer interface, up in the head group of the receptor, and made some very, very big differences up there. Also built the N-link glycans, and this again was in the old version of this, which did have support for much larger chemical space, which will come back over time. The next one was with Gregers Andersen at Aarhus University in Denmark, was these complement C4 structures. Again, these were ones I came across simply by browsing through the protein data bank and playing with structures. I actually like to do it sometimes just to relax, to be honest. And again, there were a handful of beta strands that were out of register, and six in this case. And the big section that was out actually is the location of proteolytic processing by MASP2. So it's actually a core functional region of this protein. This one, I was invited by Paul Neeson and Bjorn Pedersen while I was at Aarhus on sabbatical working on the complement C4. They asked me to have a look at this one. It was their old 3.6 angstrom, 3.5 angstrom, but very, very anisotropic membrane protein crystal from 2007, which you can probably tell by today's standards. It's actually, when it was published, I mean, they published and they said very clearly, this is a first draft. This is very, very difficult data. It was hand-threaded through this very anisotropic set. But at the time, ProCheck gave it much, much better scores than that. Its validation has become much, much better over the subsequent decade. And this one took me a month and a half of fairly solid work to really polish up, but it ended up here. And to give you an idea of the scale of the challenge of this guy, each of the little spheres on the backbone here is a C alpha atom that's actually moved more than 2.5 angstroms. So it's actually moved in register along the sequence. So there was a lot of movement that had to be done in this guy. A few up-and-coming ones. Actually, this structure is deposited now and available, but not the paper isn't out yet. It was an anti-malarial drug enzyme complex at 3.2 angstroms. There's a very, very cool 5.5 angstrom EM structure, a fairly small domain that forms actually more, not so much a microfilament, it looks more like a microtubule type structure that will be coming out at some point. I'm not quite sure when, to be honest. This one is actually published. That was fun. I was at a conference in Hobart, and Boston has been very helpful to me in many ways and invited me to help with a lot of structures. But just after a conference, heading back home, I sat down with one of his students at the airport. He'd been struggling with this one for a while. And we had about half an hour to kill, so we opened it up on the laptop. And when he took it home and refined it, the R3 was 5% lower than before. So that was nice. And this one with Michael Landsberg at UQ is by far the largest task I have taken on with this so far. Is a 4.5 angstrom, 2.5 megadalton cryo-EM complex with 5-fold symmetry. That its nearest solved relative was about 20% sequence homology. turned out to be actually very, very similar in structure, but far too distant to actually create a reliable homology model from. But luckily, considering the resolution, almost all of the structure was helices. So I could build essentially a helix at a time, apply secondary structure restraints to it, and just move it into the map one helix at a time, and it turned out to build really quite easily. It took about 2 weeks to get about 90% of that structure built. Again, that is still pending publication. I can't say much more than that about it at this stage. And acknowledgements, Mike Lawrence, for taking me seriously right at the start and helping me get started. Bosjan and Jenny Martin from, Jenny Martin formerly from UQ, now at Griffith University, for many introductions and inviting me to work on various structures. David and Jane Richardson for mold probity and their discussions, and again, inviting me a number of years back now to visit them at Duke and talk to them. Randy and Ellie, of course, for bringing me here to Cambridge. Tom Goddard, my key contact on the Chimerics team, and we've exchanged an extremely large number of emails and discussions of code. Peter Eastman and the rest of the OpenMM team at Stanford, Clipper Python team, of course, and the Phoenix team for very many discussions and input. And I'll take questions.
So thank you, Tristan. Any questions for Tristan about that?
Hi, nice talk.
Thank you.
If I understand correctly, you can't add new amino acids in your program?
Not yet.
So what's your workflow? How does it go? Let's say you have this for, whatever, 250
Okay, so that one, at that stage, yes, so that was quite clunky, you might say. At that stage, I would use Chimera to build the helix. It has a tool for building an ideal helix, so you just give it the sequence, build it as an ideal helix. I would drag that manually in close to its position as a rigid body, and then I'd actually edit the PDB file by hand to actually put them together, reload it, and move on from there. And then from that point, it was really quite easy to just move that guy into position by hand, essentially apply secondary structure restraints to that helix, and then drag either one end or via the center of mass into the correct position, and then have everything settle as it needs to go. Obviously, that can be done a whole lot better, and in this new environment, it will actually be relatively easy to make that happen. It's just I have a very long list of things to actually get through on this one.
Maybe one more. It's about this device that you're using for force feedback. How would it work for someone who doesn't have it? Can you work with the mouse?
So you can work with the mouse, and the example, the video with the cis peptide bond, I was dragging atoms around with the mouse. There are a number of other devices that you can get some that have the same capabilities of that, but are in the $1,000 range. That particular one is $250. There's still a few thousand of them available, but the company that actually made them went bankrupt some years ago, so they are going away eventually. But there are devices that are very, very similar in that $1,000 range. There's also tools that will give you essentially the same 3D capability, but no force feedback for a few $100s that I will be adding support for. But ultimately, I am obviously aware that many people will want to just keep using the mouse, so I'm absolutely committed to adding, to making sure mouse support works well, and adding as much as possible those scripted helper forces so that your actual direct interaction with atoms doesn't have to be enormous.
Very nice talk. I thought it was interesting that you're trying to do things kind of at the next generation. What about skipping a generation? So one of the interesting sort of technologies that is coming up is virtual reality.
Yes.
And I've sort of seen examples where what you do is you have some little gloves or whatever, stick a headset on, and you can actually move things using your hands, feeling forces.
That is something I'm actually very excited about, and the Chimerics team are very keen about it as well. And I actually visited them last month and got to play around with their implementation of Chimerics in the HTC Vive, which is brilliant. So that the HTC Vive is the current generation virtual reality device. And yes, you can walk around inside a ribosome. You can see a ligand in its map. And they've already got the tools. With your two little handheld devices, you can reach out, grab a ligand, and do a rigid body movement of that, for example. Taking it from that step to actually interactive dynamics is going to take a lot of difficult coding, because you need 100 frames a second graphics constantly if you don't want to get seasick in virtual reality. Which means that everything has to be in its own thread. There is going to be a lot of work to get to that point. So, but yes, it will get there. And as well as the virtual reality HTC Vive, the Microsoft HoloLens, the augmented reality, the pair of glasses, you can still see the room around you. You just have things as in the room with you as well that are virtual.
But if you compare your code to gaming hardware and software, it will never become obsolete.
Yes, yes. And essentially that's what I'm doing. Essentially that is my idea behind a lot of this. I try to make sure all of this can actually run on the laptop I bought late last year, a £1,600 gaming laptop. So it's expensive for current generation hardware. Next year, the year after, it's going to be cheap. So.
Okay, I think now we've got a question from Peter.
So clearly, you showed crystallography cases.
Yes.
Of course, the bonus is that if you improve your model, actually the phases improve and the whole thing gets better.
Yes.
Now you don't have that with the EM map. The EM map is basically as a given
it is what
thing.
it is. Yes.
And so putting atoms in density becomes a rather weak. It's not a very strong signal that you have a better model. So how do you have ideas of distinguishing how you're going to see improvement there?
So that's where, for example, things like that real-time validation with the Ramachandran plot helps. And one thing I should mention with that, so you've got that real-time Ramachandran, so you can say, okay, if I change this, it's improving my backbone conformation. But the key thing to remember is that it will not let you force fit a Ramachandran, the backbone. If you're taking an outlier and putting it into allowed Ramachandran space, but it's still energetically unfavorable, it's going to push itself straight back out. So in order to actually fit that properly, you have to actually do it right. It won't let you do it the wrong way. I mean, there are many other things you can do, and there are many other things I eventually would like to try. One of the things that I've been really keen to do is to make a lot more use of what the MD is actually doing underneath. It's calculating all the forces through every atom. So why can't I take these and actually use them to do a stress analysis on the protein and see the regions that are actually under stress? That is something I think could actually turn out to be very powerful.
Any more questions? Okay, so let's conclude this session by thanking both of our speakers once again.